Hello, everyone. Thank you so much. It's a true honor to be here with all of you in this beautiful place. My name is Jonathon Hirschi. I'm from the University of Colorado at Denver. My advisor, Jan Mandel, is an old friend of Baptiste who told me about this conference. And I'm here to share my research on transfer learning with recurrent neural networks of fuel moisture content. And I'm working on extending from a 10-hour model, which is the work that I've already done, which I'll try to describe, and then what our next steps are, which is modeling fuels of other sizes. So our objective is to provide real-time forecasts of fuel moisture content across the continental United States. The methods could be applied to anywhere in principle, though. And we want to improve on the forecast accuracy of some of the more traditionally used physics-based methods. And eventually we want to augment or replace the WRFS fire system that Adam Kocianski presented on with a machine learning model. And this image here is one forecast I generated. I can talk more I will talk more about technical details, but this is from, I also did like a point-wise deployment of a model. And I think you can still see some like rich spatial structure. So I think that, at least in my experimentation, modeling the spatial dynamics with like convolutional neural networks and stuff, I don't think you gain that much, because when you're using good weather inputs with like rich spatial structure, that accounts for most of the spatial variability, in my experience at least. But I'm interested to have more conversations about that. So across the continental US, there are weather stations with portable, or with a fuel moisture content sensor. Almost all of the available data for dead fuel moisture content is from the same standardized wooden dowel. This is one of those from one of the main manufacturers. There's another one from Campbell Scientific that uses slightly different methods. The wooden dowels are a standardized 1.27 centimeter pine dowel. This is actually half an inch, but I was too embarrassed to put inches on my slides as the American here. And so the way they deploy these is they're elevated off the ground 30 centimeters or about a foot. And so they intentionally do that to try to standardize it and remove the effect of soil moisture with directly interacting with the fuel. That makes for a nice standardized product across the US. There's thousands of these, but that might not be as realistic for certain fuels lying directly on the ground, interacting with the soil moisture. That's something I want to talk more about in the future as well. So to build a model, we've taken, this is just a spatial bounding box in the Pacific Northwest, where I'm from. I did that because I wanted a sample with lots of rain. And so at each of these locations, you have hourly resolution time series of those sensor readings. And I'm combining that with, these are both time series of the continent-wide forecasts from the high-resolution rapid refresh, the HER model. And that's also hourly temporal resolution, 3-kilometer resolution. These are the kind of set of weather predictors I use. I combine that with these like geographic features of the site, or from land fire surveys if we're predicting at a location that doesn't have a RAS site. And these set of predictors I chose because that's what most of the physics-based fuel models use, and also the weather stations have sensors for each one of these variables, so you can use it as a quality control check and also compare models that are trained with numerical weather models as predictors versus models that are trained with ground-based measurements. And I haven't observed as much accuracy difference from using the ground-based one as you might expect, so I think that's a good sign. Briefly on the architecture I use, so since we're using weather forecasts, we're assuming that the weather's known in the future, and the kind of like mapping we're learning is to map the weather at a particular time to the fuel moisture content at the same time. So the way this works is, this is like a single sample. This is equilibrium moisture content, but this will be a stack of weather variables. And so a single sample is a sequence a short time series. And we're mapping that to the fuel moisture content at the same times over a 48-hour forecast window, since that's the maximum time out that the HRRR weather model goes. And one of the nice things about this is that when you generate a 48-hour time series for each sample, you can calculate loss, and when you're trying to minimizing your loss, you're minimizing the error over entire forecast window. And I saw big improvements of that over versus like a recursive model where you just try to minimize the error at the next time step. That can sometimes lead to potentially not the optimal weights if you care about minimizing over an entire forecast window. And this is a schematic diagram. So the input comes in, there's a recurrent state, that's like the memory, the output. Inside this model, these are the layers we use, just one recurrent layer with LSTM cells. I think this would not be considered like a deep learning model, although no one agrees what that term means. But I think this was good to see. I mean, I can talk about the hyperparameter tuning I did, but I was prepared to use models with lots of recurrent layers and convolutional layers, and this is kind of a relatively simple, lightweight model that you can train and run on even a CPU, and I think that's good when you can have it that way. This is a diagram of an LSTM cell. I'm happy to go into that in greater detail if anyone wants to hear about it. Just the one thing is that with an LSTM, you have these two recurrent connections. So this one here is the long-term memory. This is the short-term memory. Everything in blue can be interpreted as a percentage from 0 to 100. Everything in orange is like a normalized signal intensity. And LSTM cells were developed to deal with a lot of the problems of training simple neural networks, the exploding and vanishing gradient problem. And so what I did was I trained a model with samples from that sparse grid of weather stations, and then with a single trained model, deploy that on the HRRR weather grid, which is 3-kilometer resolution, like I mentioned. So we did analysis to estimate the forecast accuracy for this model. So we trained over all of 2023, forecasted over all of 2024 compared to where we had observations. And we utilize a spatial holdout procedure. So in the past talk, he showed some good discussion about spatiotemporal cross-validation. This is kind of my way of visualizing it. So this is the Rocky Mountain region with all the RAWs, the ground stations. You take a random sample, you assign some to be train and test. So at the training locations, you train a model with data that's in the past of where you're going to forecast, and then you evaluate your forecast accuracy at new locations that weren't included in training and into the future. And this is just one train test split, and I repeated this process 500 times, also with different initial weights for the RNN. So that's where these plus or minus bounds come on, the accuracy metrics. It's averaged over different iterations of training and testing split. So we compared the RNN model to a couple baselines. The ODE plus Kalman filter is a simplified version of what's used in the WRFS fire system. The XG boost, seems like everyone's using XG boost here, which is cool to see. But this was a static or a non-recurrent model. So it's just taking the weather at a single time, outputting the fuel moisture content at a single time. It has no memory of what that past trajectory of the fuel moisture is. And finally, a kind of simple climatology method, just a historical average of the fuel moisture at the same time and same location. And by the RMSE, the RNN performed pretty well compared to the others. This is the overall error when you average over all locations and all times, all replications. I didn't include it on the slides. When you break it down by moisture levels for like dry fuels and wet fuels, you see there's different error thresholds for those different levels, which is something I want to explore in greater detail. And so there's a lot of ways we might consider still improving this model. So the main is adding these satellite data products. So the reflectance bands from VIIRS, basically the red-green like channels I want to consider, as well as soil moisture satellite products. And an important thing is the initialization. So when I'm calculating forecast accuracy for the RNN, when I start the forecast, I'm calculating that accuracy from like time 0. But I think it would actually look better as if you had a spin-up period, like another dynamic model, but that'll be in a follow-up study. Finally, another thing that I've done, this was something I developed in my master's a couple years ago, and I can apply this to the RNN, but those accuracy metrics I showed before was with standard mean squared error loss. But one thing I've been experimenting with is using custom loss functions that account for a couple of things. So first of all, this like S-shaped curve you see here, this is like the idealized relationship between fuel moisture content and rate of spread. This is rate of spread predictions from a Warfest fire run when you keep wind speed and slope and a bunch of other things constant. And so what you can see from here is that in the dry region of fuel moisture, you have huge differences in the rate of spread. So for instance, if you predict that the rate of spread is, or that the fuel moisture content is like 3%, and really it's like 2%, that leads to a huge error. Same with the other direction. But if you predict that the fuel moisture content is 30% for this fuel type, and in reality it's 50, it's both so wet that they're not expected to burn anyway. So I kind of want to use this pattern to inspire a way to weight the model errors to get a model that prioritizes accuracy in that dry region. It's kind of like you allow some larger modeling errors for the wet domain because you don't think it's going to be as important. And another motivation for that is these are the reported error metrics from Campbell Scientific for this for their sensors, and you can see that the error rate grows as the fuels get wetter. So normally in machine learning you minimize all your errors equally, but I think it makes sense for modeling dead fuel moisture content to prioritize accuracy in that dry domain, partly because of its relationship with wildfire rate of spread, and also because those sensor readings are more likely to represent reality. So that's what I've done so far in my research, and now I want to describe what we're planning to do next. Fuels can be any size. We use these idealized classes, 1 hour, 10 hour, 100 hour, 1,000 hour. In reality, I included just like a picture of some real fuels. There's this very complicated mix of different sizes and shapes and species. So I think what I've done with like this model, I think like the most humble way to view it is this is a forecast of what a sensor will say. It's not a forecast of what reality necessarily is. So connecting those sensor readings to reality is a much larger research project. So I'm going to describe a few different methods that are all kind of referred to as transfer learning. And as of now, my plan is to kind of compare all these different approaches. So I'd love to get some feedback. If one of these ideas is stupid, that'd be great to know because it would save me some time. So first, I want to describe about what type of observations we have of fine fuels, designated as 1 hour fuels, and then large 100-hour fuels. And so first we have controlled academic studies. So these tend to be very small scale. This is a field study in Oklahoma in the United States that was done in the mid-90s. This one study has been used to calibrate multiple different physics-based models. The Nelson model, there's a model by Vanderkamp, Canadian researcher, that's a really cool model. And so this like one kind of limited study has been used so many times I actually reached out to Carlson, the original author, trying to get that raw data set, and he's retired now, but he told me that the data had been lost in a fire and was gone forever, which I thought was kind of interesting, but I was able to find someone who'd used the data for their own calibration and they had it backed up, so we were able to save that data. And so there's some other small scale studies, but there aren't as many as I was kind of hoping to find. And these are what the data look like from the Carlson study, just one stretch of it. So they're measured twice daily resolution and weather from a portable weather station at the same location. And you can see that they also elevate the fuels off the ground like I was describing before. So the nice thing about this is that it's very standardized. We know like exactly how they took these samples, the exact dimensions. The measurements are very reliable. The downside of studies like this is that, again, they're less representative of fuels lying on the ground and there's not that much data. The other type of observations we have for these different fuel types is field samples. In the United States, this FEMS organization has an API for all sorts of different fuels that they measure. These are some of the images of the types of sizes and shapes you would see of what someone classifies as a 100-hour fuel. But you can see there's a lot of variability even within that one bin of the exact shape. And these samples are taken once every 2 weeks usually. And so again, the positive side of these types of samples is that this is real world stuff. It's lying on the ground, it's interacting with the soil moisture. But the downside is that there's a lot more uncertainty about the sampling methodology, the exact time it was sampled, the fuel size, species, all these different things. This is just a map of some of the sampling locations. There's a lot of sampling in the western United States, almost none in the eastern United States. There's less fires there. So the transfer learning is a very general term for a set of methods where you train a machine learning model on one task and then use the same model, fine-tune it for a new task. So the very general idea is that we're going to pre-train a RNN model on the 10-hour sensor data and then retrain it to predict, to provide forecasts for these other fuel types. And I'm going to describe a few different methods of how I plan to do that. To step back a bit, how do we do it in physics-based models? So in physics-based models, they typically have parameters that account for fuel size. And this kind of central assumption in a lot of the models is that the physics is exactly the same for a small stick and a large log, and that the only difference is the rate of change, like the time scale of the dynamics. And that's a pretty strong assumption. So this is kind of what that looks like, where you have this theoretical equilibrium value, and the fine fuels will approach that, equilibrate with that very quickly, whereas the larger logs will take longer to equilibrate to that exact same level. And so this is a very simplified version of a time lag model. And so this parameter t, you just crank it up and down and you get a 1-hour model or a 100-hour model. And so this is convenient in order to provide, to model the fuel moisture content of any fuel size, but it makes this kind of strong assumption about the physics. One of the methods that I'm hoping to use is calling it temporal downscaling. So this is that same data I showed you before, which is twice daily from that Oklahoma study. And this black curve is what a physics-based model fit to the data with like optimal parameters in that window would do. And you can see like this type of like spike here, because 1-hour fuels would change very quickly. If you were to try to train a model, pure statistical model on these green points, like how is a machine learning model going to learn that there should be this like spike and fall that's just not there in the data? So I'm hoping to use this, and what I think is that certain physics-based methods might be less accurate than recurrent neural networks or other models for like long-term forecasting. But when you use them for historical reconstruction, like you're just fitting between known points, they can be pretty useful, and it's basically like a physics-informed like interpolation method. And so my current efforts are to take these lower temporal resolution data and fit curves that are solutions to physics-based models to those points, and then use that to retrain the 10-hour model, because that, as currently constructed, those accuracy metrics I showed you, it's expecting hourly resolution data. And so the most straightforward way is to get hourly resolution data of these other fuel types, but we don't actually have those in reality. So I'm trying to use physics-based models to construct those. Another option is a family of models called continuous time recurrent neural networks. They use this really cool idea called neural ODEs, which instead of the normal kind of backpropagation algorithms that are used within neural networks, they pose the recurrent connections. Remember I showed you that image of an LSTM that had the arrow pointing to itself? They model that as a differential equation and then use normal like ODE integrators to update the model weights. And the cool thing about this is that you can run, so like the model I showed you that was trained on hourly resolution data, I can only ever run it every hour. But with continuous time RNNs, you can change the time step like you would in any other dynamic model. And that could be really useful. So one of the benefits of that is I probably want to learn how to do that anyway, because for instance, in Warfest Fire, a lot of the simulations are run on every 15-minute time steps. And over those short times, with very fine fuels, if the weather is changing really quickly, the fine fuel moisture content could be completely different even on a 15, 30-minute time scale. So what the idea would be is you train a model on 10-hour fuel moisture content and then just run it at a much faster time step and then say that's your model of 1-hour fuels. And so I think that's a cool idea. This is kind of like, I think this would be like the most fun to work with, but one of the downsides is that, again, it relies on that assumption that the physics is the same for twigs and logs, which, part of the motivation of using machine learning models built from data is so we don't have to make specific, like restrictive physics assumptions like that. The last method I'm going to talk about is what we've been calling physics-initiated RNNs. This was something that my advisor Jan initially worked on, so this is a solution to a simplified differential equation for fuel moisture content. It's just a simple time lag, so this is like an autoregressive lag1 model. And if you go in and set the weights directly, you can exactly reproduce this model in a single RNN cell. This is a simple RNN cell, and if you follow the arrows with these weights, you end up with the exact same physics-based model, which I think was really cool that we can directly code in the solutions to differential equations into recurrent neural networks. And I can do the same thing with an LSTM cell. It's much less straightforward because look at all these crazy arrows going around. And so the idea is that if you don't have enough data to get a machine learning model to converge to a good solution, the idea is that you initialize it with the solution to a physics-based model so that it's already maybe close to an optimal solution, and you can get there with much less data if you don't have enough data. So this is something I'm also going to try with, so I pictured this with a 10-hour time lag, but you can just change this number to 1 or 100, and so I can code up a 1 or 100-hour LSTM cell and then train it from there, and hopefully it's closer to an optimal solution. So those are kind of all the main ideas I have. They're all in development now. I look forward to hopefully getting some results soon. One other idea I kind of just wanted to float, I know less about this, but I'd be interested in having some conversations about this, is I'd like to see fuel models that have dead fuel moisture content changing like vertically, because again, so this is a picture of a forest with this is like a ladder fuel that's standing dead. You have all this dead material vertically. And so what I think would be interesting is that for the dead material that's on the surface, you incorporate soil moisture, and it's maybe more directly represented by those physical samples that are taken off the ground. But for this elevated dead material, that might be better represented by the sensors that are elevated off the ground. And so having dead fuel moisture content vary vertically, I think would be interesting. It would take a lot of work to make that physically reasonable, but that's a future idea I'd like to develop if anyone's interested in it. Thanks a lot to collaborators at WIRC, where Adam is from, and some NASA grants, and there's some great data packages in Python that are made by Brian Blaylock. It's really easy to access all this public data. Thanks a lot for sharing, letting me share.